Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In our last video, we showed you how to use OpenMP to perform matrix multiplication with a multi-GPU parallel computing method. In this video, we will provide a detailed demonstration on how to use a Fortran program to check the accuracy of our multi-GPU parallel computing method for matrix multiplication. We'll guide you through a process to detect any errors in this method. In our previous videos, we demonstrated how to execute jobs using a job script. Like in our initial videos, this video will also cover executing interactive jobs. Normally, we set up our software environment within the job script using the module load command. However, for interactive jobs, we need to ensure that the correct software environment is manually loaded. After logging into Saga, I can view my default software environment by executing module list. You might recall from earlier discussions that I created an alias in my bash rc file to load the latest Intel Fortran compiler. This alias includes the module purge command, which clears all currently loaded modules, thereby completely altering my software environment. Let's activate this Intel alias to update my software environment and then use module list to verify the changes. Interestingly, you'll notice that the environment hasn't changed. This is because I previously used module save to make the Intel software environment my default setup. To verify the accuracy of the multi-GPU parallel computing for matrix multiplication, we will execute the Fortran program from our last video one more time. This time, we will save the matrix C to a data file and use this file to confirm the correctness of the calculations. As you can see, this Fortran program is located in the GPU parallel OpenMP directory within my work folder, and any changes to the program are saved here. To submit our job to the Slurm workload manager, we use the sbatch command, which assigns it the job number 11802617. By executing the sq command, we can monitor the job's progress and see that it has been running for 9 seconds. After several checks, we confirm that the job has finished. The process takes additional time due to the output of matrix C into a data file. We can use the ll command to verify that the job has created the data file, which we find is over 7 GB in size. Therefore, it was crucial to submit this job from the work folder because of the large file size. We need to execute the Fortran program from our previous video, which utilizes a single GPU to output matrix C. This will serve as a reference for the matrix multiplication. To do this, we open the Fortran program and set the write variable to 1. We also need to revert the testing Python script to the version used in our previous video to properly execute this Fortran program. Additionally, we should adjust the job script to request 1 CPU core and 1 GPU, as was done previously. The Fortran program and the testing Python script from our previous video are located in the directory named OpenMP on A-100. To submit our job to the Slurm workload manager, we use the sbatch command, which assigns it the job number 11802241. We can monitor the job's progress by executing the SQ command and see that it has been running for 11 seconds. After several checks, we confirm that the job has finished. We use the ll command to check if the job has produced the data file, finding it to be over 7 gigabytes. We then rename this data file to C16384 and use the ll command again to ensure the file name has been updated. In the work folder, I have created a new directory named error, which houses one Fortran and one Python program with similar names. We'll begin by opening the Fortran program in the Emacs editor. This program works with two matrices, C and D, and accesses 3 data files. The first, C16384, is matrix C generated by the Fortran program using a single CPU core and 1 GPU. The second file, simply named C, is matrix C produced by the Fortran program that utilized 16 CPU cores and 2 GPUs. The third data file is called error. First, we load the matrix generated by the Fortran program that used a single CPU core and 1 GPU, and we store it as matrix C. Next, we load the matrix produced by the other Fortran program that operated with 16 CPU cores and 2 GPUs, and we store it as matrix D. We calculate the difference for each corresponding element in matrices C and D, and then sum all these differences. If the matrix multiplication performed by the program using 16 CPU cores and 2 GPUs is accurate, this sum should be 0. We record this sum in the error data file, and we can then verify whether it is indeed 0. Let's now open the Python error script in the Emacs editor. This script interacts with the Fortran error program and compiles it using the Intel Fortran compiler. The Python script specifies compiler options to compile the Fortran program, and then it executes the resulting executable. Additionally, we will use our Python setup script to compile and execute the Fortran program on a compute node utilizing a single CPU core. First, we need to transfer the data file C16384 from the OpenMP on A-100 directory to the error directory. We can use the ll command to confirm that the file has been successfully moved. Next, we'll move the C data file from the GPU parallel OpenMP directory to the error directory. We can again use the ll command to check the movement. After that, we execute our setup script to switch to a single CPU core on one compute node. Specifically, we ended up on the C559 node. With this setup completed, we are ready to execute the Python error script. When I logged into the Saga Linux cluster, I demonstrated that my default setting is the Intel software environment, which includes the latest Intel Fortran compiler that will be used by the error script. Let's execute the Python error script. First, the script prints out the compilation command. After this, you will see many messages from the Intel Fortran compiler in your terminal. Look for the message, relocation truncated to fit. Large static variables or arrays can sometimes cause this issue if they are placed in memory, such that they exceed the 2 GB limit. Why didn't this issue occur in our previous videos? The error Fortran program is different from the Fortran programs we used before. In those videos, we use the OpenMP or OpenACC libraries in the Fortran program. When the Python error script tries to run the compiled program, you'll see the message, "No such file or directory." This is because the compilation failed due to the relocation truncated to fit error. To fix the issue with relocation truncated to fit, we can use allocatable arrays. Allocatable arrays in Fortran are dynamically allocated at runtime, rather than being statically allocated at compile time. Let's create a new Fortran program, named with the suffix allocate. In this program, we'll declare the matrices C and D as allocatable without initially specifying their dimensions, n. Later, we'll allocate these matrices with dimension n just before they are used. In our Python script, we'll modify the file name of the Fortran program to use the one ending in allocate. We'll use our setup script to access the C559 node. On this node, we'll execute our Python error script on a single CPU core. The script will display the compilation command, and now the compilation was successful. The Python script will execute the compiled Fortran program, which may take some time as it processes large matrices from the data files C16, 384, and C. Once the program completes and the command prompt returns, we can exit the compute node. We can use the ll command to check if the Fortran program created a data file named error. Next, we'll use the more command to inspect the number inside the data file. Unfortunately, the number is not 0, indicating an issue with our multi-GPU parallel computing method. In our next video, we'll address this problem and develop a new approach for multi-GPU parallel computing. I am looking forward to the next video, wishing you all happy computing in the meantime.